it's always a pleasure to be in this outstanding institution. My family owes or has relations with this place. At least 4 people have their education here in the Technion. And so today I will be telling you, as Amit said, about gravitational waves and the two-body problem. But before that, I want to mention that my research is not only in the field of Einstein's gravity, but also in high energy physics. And I oscillate between the two fields. As you will see, this talk today will combine high energy physics, namely field theory, with Einstein's gravity. And this work describes a bit of older work which I did. Currently, I'm working on evaluations of Feynman diagrams. This is a very interesting and very nice mathematics and geometry, but we won't go into that today. So what is the outline of the talk today? I will discuss the detection of gravitational waves briefly, because I know some of you have heard it. And then I will explain the theory, or a very beautiful theory behind it, the theory of the two-body problem in Einstein's gravity. And we'll see how it can be solved using ideas and tools from quantum field theory, such as Feynman diagrams. And that will be, in fact, the third subject, the effective field theory approach. So please feel free to ask questions. Here is the announcement from February. I hope it was audible. This is as much excitement as you'll see from a scientist. This is David Brightside, the chair of the LIGO collaboration. Okay, so what is the excitement about? Here is the detection paper, PRL, from the following day, February 12th. It's titled Observation of Gravitational Waves from Binary Black Hole Merger. Now, the abstract is so good that I'm just going to read it to you. I want to mention before that there is also an Israeli author of this collaboration. There's about 1,000 people on this collaboration. But one of them is Israeli. His name is Prof. and his undergraduate degree was from the Technion, and his PhD was supervised by myself and Tzvi Piran. And he just joined that group. Okay, so the title is Observation of Gravitational Waves from a Binary Black Hole Merger. First sentence. On September 14th, 2015, at this universal time, the two detectors of the Laser Interferometric Gravitational Wave Observatory simultaneously observed a transient gravitational wave signal. The signal sweeps upward in frequency from 35 to 250 Hz, with a peak gravitational wave strain of 10 to the minus 21. The whole signal is about 200 milliseconds. Next. It matches the waveform predicted by general relativity for the in-spiral merger of a pair of black holes and the ring down of the resulting single black hole. Okay, so I want to make sure we understand what's the physics that's going on here. There are two black holes orbiting each other. As they orbit, they lose energy. Why do they lose energy? Because they emit gravitational waves. So with time, they get closer and closer. As they get closer, the frequency goes up and the amplitude goes up of the waves emitted until they finally collide and merge. Okay? That's the system that created this signal. The source lies at a distance of... Okay. The source lies at a distance of about 1.2 billion light years. The initial black hole masses are 36 and 29 solar masses. This is amazing as well. With 3 solar masses radiated in gravitational waves. Okay, you can compare it with the Hiroshima bomb, which was less than 1 gram of energy released into energy. Here, 3 solar masses were converted from mass to energy. These observations demonstrate the existence of binary stellar mass black hole systems. And the final sentence, like exclamation mark. This is the first direct detection of gravitational waves and the first observation of a binary black hole merger. Okay, so that's the detection paper. So here is a picture of two black holes. Here this is an artist's impression, of course, it's not a photo. And they're not white. Black holes, we expect them to be black. And these spirals are supposed to denote the spirals of gravitational waves which are emitted from the system. Of course, it doesn't spiral only in the plane. In fact, most of it goes out of the plane, but in order to draw it, they had to draw it only in the plane. So you see them orbiting each other and emitting gravitational waves as a result of this motion. This is the system that emitted the signal. And here is the signal. This is the big thing, okay? There are two detectors, one in Washington State, the other one is in Louisiana. They both received very similar signals, which gives us strong evidence that it's not some local effect that happened in one of the places. And it all lasted, we don't have here the scale, but it's about 200 milliseconds. And you see here a periodic signal, which becomes higher in amplitude, higher in frequency, and then rings down. The two are similar. What happened here? This is the point where they merge. Okay, these are the 4 or something less revolutions before they hit each other, and then you create a peanut-shaped black hole, which starts rotating, and then it very fast relaxes by emitting further radiation, and you get a stable, stationary black hole here. Okay, with the noise level. Okay, so this was the signal. This was unbelievable because it was just like all the textbooks told us that we should expect such a signal, but we were looking for these signals for decades of years. And for decades. Okay. How does one detect a gravitational wave?
What does it mean, the end of the signal? What happened at the end of the signal?
A big black hole was created. One big black hole created out of the merger of two smaller black holes. Okay?
How the distance was determined? Where did it happen? Because I understand there was no light.
Yes, okay, so I will comment on that. The question was, how do we know about the parameters of this system? From the signal itself, one can get there. The first thing you can see from the signal is f dot divided by f, where f is the frequency, f dot is the rate of change of the frequency. From that you get immediately, just from quasi-Keplerian physics, the masses involved. And from that you get that the masses involved are 30 solar masses. And then by a more refined analysis, the amplitude of the signal and more refined features of it, comparing it with full simulations of Einstein's gravity, you can get a good estimate for the rest of the parameters. Let's see how does one detect these things. So you have such a machine in the American desert, made out, it's an interferometer. It has 2 arms in which laser beams are going back and forth. Of course, it's in vacuum and in some concrete building. And you want to measure relative changes of the optical distance between the 2 arms. This is what an interferometer does. The light there is about, visible light, about 1 micron. So you think you can detect a relative distance change of the 2 arms of about 1 micron. However, the sensitivity there is amazing, the signal to noise is amazing, and they can actually detect 10 to the minus 12 of a fringe. So they can detect amplitudes of 10 to the minus 18 meters. That means at the frequency about 100 hertz, as we saw something between 30 and 250, 10 to the minus 18 meter is 1,000th of a nucleus, right? Okay, so it's a very tiny oscillation of the mirrors. The optics is so great that it can detect it. And the reason you need such a sensitive machine is because gravitational waves arriving at the Earth are so weak. Okay, here's an explanation how it works. So this is an explanation from a late night show in the US And you'll see how an interferometer works in principle, and I hope it will give you an idea how it works. Oops. Okay, so what did we see there? There was an interference pattern made out of the two arms of the interferometer, and instead of a gravitational wave, they sent a sound wave, which changed the relative optical distance of the two arms, and that shifted the interference pattern. That shifted the interference pattern by several patches, which we call fringes. So in the actual experiment, the arms were 4 kilometers long. What made the change was the gravitational wave that came from space, and the movement was not by a full fringe, but by 10 to the minus 12 of a fringe. So it was a very tiny movement, but the instrument was sensitive enough to capture. Okay, now this closes very nicely a 100-year story and 100-year prediction of Einstein. Einstein announced his relativistic theory of gravity, which he called general relativity, in Berlin in November 1915. And later on he wrote this famous manuscript, which today is held at the Einstein archives at the Hebrew University by his will. And then he immediately realized that if gravity is relativistic, then a change in the position of a mass will not change the gravitational field immediately, instantaneously, or instantaneously throughout the universe, but the knowledge about the change of the location can propagate only at the speed of light, and therefore there will be a phenomena of propagation of gravitational field, namely a gravitational wave. This is, of course, a new kind of wave, different than all the kinds of electromagnetic radiations that we know, and he published this prediction a few months later, in 1916, in this paper. Now, there was a very long story. One can tell actually quite a number of stories about this detection of gravitational wave. There was the story of the development of our understanding of gravitational waves. Einstein himself had misconceptions, and then many of his followers. Then there was a big story about how the machines were developed to be able to detect gravitational waves, which is also an amazing story. But today we will not discuss either of these stories, but we'll go to another story. How do you analyze the theory of the motion of this system, of the system made out of two compact objects, say two black holes? So I should mention that this is the first direct detection, but before it, already since the 70s and the 80s, we had an indirect evidence for gravitational waves that came from high-precision slowdown measurements of binary pulsar, which was found to be consistent with the energy dissipation due to gravitational waves. So this is related to the pulsar discovered by Hulse and Taylor in '74, and they won the Nobel Prize in '93 for that. So that's a system made out of two stars orbiting each other every 7-something hours. One of them is a neutron star rotating around itself 70 times a second, 70 hertz. And then with time, they slowly get closer to each other because they lose energy to gravitational waves. And their measurements are so precise that they can measure this very small increase in time of frequency, or very small shortening of the year. Okay, their year, the time of orbit, is this 7 or 8 hours, and by measuring that, you find indirect evidence for the existence of gravitational waves. But what we had this year was the first direct evidence for the waves.
It's not a slow down.
It's a speed up, yes. I meant the year becomes shortened. So it's a speed up, I agree. Okay, so now we confirmed Einstein prediction, in two ways, maybe. First, it's a first strong field test of general relativity. General relativity is with us for 100 years. We had already quite a number, maybe a dozen or so, experimental confirmations, but this is the first one for strong field, where the black holes, there's strong gravity close to the black holes and they collide. And this is the first gravitation of another strong another important prediction, the prediction of gravitational waves. Okay, so it closes this story of 100 years, which is quite amazing. And to me, it shows us the power of a true idea. Okay, there was one person, Einstein, sitting, thinking about these things deeply. He got the theory, and he got the correct idea, but it was much ahead of the technology of the time. And with time, more and more people joined this idea, more and more insights and hard work went into it, until finally it got realized. But it's not only closing a loop with the history, it's also opening a window to the future, and that's the next important thing about it. What is it opening? It could be the beginning of a new era of observations through gravitational waves. So today we can see in the visible, in the IR, in the radio, in the Röntgen, but now we can see something completely different, completely different kind of wave. And the first signal already surprised us, because we never imagined that, we never had evidence for such systems. Two black holes, 30 solar masses. I don't know if we had, this is a unique system that was discovered. And people are building more detectors around the world. There's the LIGO detector in the US, which made the detection. There's a Virgo European detection in Italy. In Japan, there's a smaller one, but they plan an important upgrade. They plan 2 additional detectors, interferometers in India and Australia. The importance of having several detectors is in order to find spatial resolution, in order to be able to locate the place the signal came from. It's like the fact that when we have 2 ears, we can tell a little bit where sound is coming from. And there's also a more ambitious plan to build an interferometer in space where the length of the arm will be millions of kilometers. And the Americans dropped it, and now the Europeans are following up, and they already sent kind of what they call a pathfinder, so a mission that is testing some of the technologies needed for this interferometer. In the future, we might see gravitational waves not only from sources like this, but also coming from the Big Bang and other sources. In principle, there are 2 kinds of sources, astrophysical sources, either steady state sources that come from a constant revolution, or high short bursts of gravitational waves coming from explosions, mergers, collapses, strong effects. Okay, so this was hopefully representing what happened, what was announced in February and happened in September, and to give us a good idea what